A very good morning, students. This is Dr. Shanti Makka, Professor in the Department of Computer Science and Engineering at Vardhaman College of Engineering. Today, we are going to discuss different methods which are used to sort an elements, maybe in alphabetical order, maybe in ascending order. The data may be of an alphabets, or we may have the data in the form of the numerical values. Maybe we need to sort the data or the files based on the size of the file, or else we have a different various. Like, let us understand first what is the purpose of sorting, then let us go through what are the various methods which can be used in the field of computer science to sort the given data. The outline of my presentation will be introduction of sorting. Then I am going to start with an example of bubble sort, and in the bubble sort we are going to discuss the example and program, then we are going for the analysis. Okay. Now, what is sorting? Basically, it is a fundamental operation in computer science, and we can also say that it is a fundamental operation in the data structure to arrange data in a specified order. To arrange the data in a specific order. The goal of the sorting is to arranging this collection of elements in a way or such a way it makes certain operations such as searching, retrieving, analyzing the data very effectively. And this is also used in databases, different various searching algorithms, file systems, data mining and analysis, in networking, in routing, and we can also use it in the graphics rendering, genetic algorithms and operating systems. What are the key concepts we have to discuss while sorting any particular data? First key concept is ordering criteria. The sorting can be done based on these certain criteria, such as we may have the numerical values or alphabetical order, or maybe based on the dates or the custom defined criteria. The chosen criteria always determines the arrangement of the elements. Stability. What do you mean by stability while talking about the sorting? Like, the stability maintains the relative order. Again, what do you mean by relative order? Relative order means, for example, in a given data, we may have the same data in different places. For example, I have the element 2 in my data placed in the position number 2 and position number 5 and the position number 10. The value is 2 only, but it is placed in 3 different positions. So while sorting the elements, we all know that these 3 2's has to come in consecutive locations. So in the given array, the 2 which is placed in the 2 has to come in the first as compared to other 2's. So in that way, we have to maintain, we are going to maintain that relative order. So that is also one of the factor we have to, we consider as a key concept in the sorting. Now, what are other factors we have? In place versus out place. We also have comparison versus uncomparisons. In place means when we are sorting elements without having extra memory space, we can arrange our data. That means we take one array, we apply the sorting procedure, and we are going to have the sorted array also. Everything is going to be done in the single array. And in case of out of place, where we have to create another data structure or the new sorted data structure, where the elements are going to be sorted and finally we get it. Like, we need an extra memory space. Apart from the input array, we need to have another extra space, that is out of place. And another criteria or the key concept we have is comparison versus a non-comparison. Comparison means we compare the elements, like we make a comparison between any two elements to get that sorted order. But still we have a certain approaches where without comparison also we can arrange our elements. So that those algorithms comes under the category of non-comparison algorithms. Like we have a counting sort, radix, as well as the bucket sort. These are well-known, popular examples of non-comparison sorting methodologies. The common sorting algorithms we are having, let me list here, like bubble sort, selection sort, insertion sort, quick sort, and merge sort. Bubble sort means definitely we are going to have an alphabet. We may have the alphabetical alphabets also, or we can also go with the numerical values. I'm going to demonstrate a bubble sort concept by taking the input as a numerical values. By using bubble sort, we can arrange the data either by in a ascending order or the descending order. Based on the required sequence, we have to make a certain modifications, okay, to arrange the given numerical values in an ascending order using the bubble sort. As I mentioned, we are going to take a data and we will be like explaining like each pass, like how the elements are going to be compared and everything. Entire process we are going to demonstrate, okay. But remember that the data we are arranging in a ascending order, okay. So let me take a small example to brief you. Here you can see I have taken the number of elements as 5. I've taken the number of elements as 5. The elements are 10, 5, 3, minus 2, 6. Okay. Now, how these elements are going to be arranged in an ascending order? How these elements are going to be arranged in a ascending order? In bubble sort, we make a comparison between adjacent elements. We make a comparison between adjacent elements. So first two elements has to be compared first. So the first two elements means 10 and 5. If this element, the first element is greater than the second element, we have to swap these two elements. What are we doing? We are going to compare the adjacent elements. First element will be compared with the second element. If the first element is greater than the second element, we have to swap these elements. Okay? Now it's going to be 5, 10, 3, minus 2, 6. Fine? Remember, in every particular step, we have to remember how many comparisons we are doing also. Okay? Now we have to compare every adjacent elements. We have to compare, no? Like as first and second has been compared, now the second and third has to be compared. Fine? Now here also you can see, as I mentioned earlier, if the previous element is larger than the next element, we have to go for the swapping. This the 10 is greater than 3, so we have to swap 5. 5 will be copied as it is, okay? 3 and 10 will get swapped. So this is the next step. Now again compare this 10 and minus 2. Again you can see here 10 is greater than minus 2. What are we going to do here? We are going to swap again. If you observe this process, my aim is to bring the largest element at the last position. Why? Because I am arranging my data in an ascending order. Ascending means smaller to the higher. So the largest element has to come to the last position. So that is what I am doing here. I am making comparison between the adjacent elements and I am bringing the last element, the largest element to the last position. Okay. Now again, let us again repeat the same process. Compare this 10 with 6. 10 with 6. Fine. Now 10 is greater than 6. What are we going to do? We have to go for the swapping. Now you can see here, like all elements, all adjacent elements has been compared. At the end, we got the largest element at the last position. So just to differentiate, the elements which are already sorted, I am keeping them in a square. Okay? Why? Because in the rest of the steps, I no need to think of 10 because 10 is already been taken its position. Because in this, the entire process, what I did is, I got the largest element to the end. So, largest element to the end means, no need to touch that element in the rest of the process. You understand? So, this is, this entire process is considered as the pass 1. Fine? Pass 1. In the pass 1, we are going to have one element in its right position. Fine. So, now try to keep a track of the number of comparisons, how many comparisons we have done here also. You can see here one comparison we did, here second comparison, here third comparison, this is the fourth comparison. Okay, how many comparisons we did? We did 4 comparisons. And remember that the number of elements we have here is 5, and in the past one we did the 4 comparisons. Fine? So now let's continue, because only one element is sorted, no? We have to go for the rest also. Only one element is sorted. Fine, you can copy the data from the past one to continue with the past 2. So what is the data we have here? 5, 3, minus 2, 6, and 10. Please remember that 10 is already sorted. We won't be using the 10 in the to make the comparison with the data in the past 2. This is past 2, okay? Let us take past 2 here. So what are we going to here? What are we going to do here? Compare these two. Guys, when are we swapping? When the previous element is larger than the current element. But here 5 is larger than 3. So what do we do? Again we have to go for the swap. So this is 3, 5, minus 2, 6. Copy 10 as it is. Fine. Now again compare these two elements. 5 and minus 2. 5 is larger. So larger means we have to go for swapping. So 3 minus 2, 5, 6, 10. Fine. Now again compare these two, 5 and 6. Is 5 is greater than 6? No. But still we made a comparison, that makes sure, okay? If it is greater, then we go for swapping, or else the data will be same position, okay? So just copy it again. 3 minus 2, 5, 6, 10. Fine. You can see in a second step we got the next largest element in a right position. So how many comparisons we did in the past 2? Just make a note here. 1, 2, 3. How many comparisons we did? See, we are not going to make any comparison with 10 because 10 is already sorted. How many comparisons we did? We did 3 comparisons. How many? 3 comparisons. Fine. Now let us go for the next pass. Nothing but pass 3. Again, copy the data from the previous step or the previous pass. That is 3 minus 2, 5, 6 and 10. But in which already 6 and 10 are sorted. You may be thinking the 5 is also sorted, no? But we cannot make sure. We have to check it. Okay? We have to check, then we have to confirm that 5 is in its right position. Now we can compare these two. 3 and minus 2. 3 is greater. What are we going to do? We are going for swapping. Minus 2, 3, 5, 6, 10. Fine. Now we can compare 3 and 5. If the previous element greater, then only we go for swapping, but here 3 is less than 5, we won't go for any swapping, but we have to make a comparison to to understand that this element is smaller than this, okay? Minus 2, 3, 5, 6, 10. You can see here 5 is in its right position, okay? Now let's go for the next pass. Before that, what are we going to do here? We need to write the number of comparisons. How many comparisons we did? 1. This is 1. This is 2. How many? We did 2 comparisons. Fine. Now let's go for the next pass, which is pass 4. Pass 4. Afterwards, we'll make a note of number of comparisons. Just get the data from the previous pass, that is -2, 3, 5, 6, 10. You can observe very much clearly, like these three are already sorted. Just keep them in a square box. Now we have to make a comparison between these two. If this element is larger than this, then only we go for the swapping. But in this case, -2 is smaller than this, so we just copy as it is. So 2, 3, 5, 6, 10. How many comparisons we did? Only one comparison. How many comparisons? One comparison. So as these are all like, these 4 elements has taken its own position, so we left with only 2. Definitely if the list is having a one element, it is sorted. When we have more than one element only, we need to apply the process. Okay, so this element is sorted here. Now please, when we have the number of elements as 5, how many passes we worked? 4 passes. You can see here, this is the pass 1, this is the pass 1, and this is pass 2, and this is pass 3, and this one is pass 4. How many passes we worked? 4. For 5 elements, 4 means how many passes we have? N minus 1. How many? N minus 1. So the number of passes are 4. But if I have to express in terms of n, it's going to be n minus 1. In each pass, how many comparisons we did? See, in the pass 1, 4 comparisons, and pass 2, 3 comparisons, pass 3, 2 comparisons, pass 4, 1 comparison. If I have to express the number of passes in terms of n and the pass number, if I have to express the number of passes, number of comparisons in terms of n and the number of pass number, you can see here it is number of elements are 5 here. What is the pass number? 1. So 5 minus 1 equals to 4. Clearly observe it. And here n is what? 5. 5 minus 2 is 3. And 5 minus 3 is 2. 5 minus 4 is 1. So that means number of comparisons equals to n minus p. You need to understand this fact so that we can easily write a program. Okay? Number of passes are n minus 1. Number of comparisons in each pass. This is in each pass. In each pass. Okay? Number of comparisons in each pass is n minus p. Okay? I hope you understood the concept. Now let us move to the program. Same, the way I have explained the concept, by following the same sequence, I am going to write a program here. Fine? We will be writing a program in C. So which header file we are going to include? Hash include stdio.h. Fine. Then take the main function. Now we are going to sort these elements using bubble sort. That means we need to have a collection of elements. I am taking an integer data at maximum 10 elements. Number of elements, one that to represent the number of passes I am taking p, and to refer the elements I am having an index variable as I. And we have to go for the swapping also. When we are swapping 2 elements, we need to have one temporary variable. And let us see that further any more variables are required or not. At the beginning, I just declared few variables here. Let's see, based on the, depending upon the need, we can add the variables, okay? Now first, I have a printf statement. Printf, enter number of elements. Enter number of elements. Fine. So, when this message displays on the screen, I have to take some input from some numerical value, some positive value for the input size. So which I'm scanning, scan of percentage D ampersand 10. That means I'm going to give some input size. Remember that this size must be less than or equals to 10. The reason behind, I have taken the maximum capacity of A as 10. Fine. Now I have the number of elements. Now I need to have that many number of elements in my array. Now I need to have that many number of elements in my array. Fine. So now we have to import an array. Fine. For I equals to 0, I is less than n, I plus plus, scanf, percentage D, ampersand, A of I. Okay? Now I equals to 0, less than n means we are going to take the element into the A of 0 place, and again I equals to 1. Like this we are going to keep the elements from 0 to n minus 1 index. So input is there. Now we have to apply the sorting approach. Okay. Let's take here as bubble sort begins. Bubble sort begins. See, for each pass, n minus p comparisons. How many passes total? N minus 1. So I'll take one loop for the number of passes. The variable which I have taken for the passes as here already declared as p. P equals to 1. P is less than or equals to how many passes we have discussed? N minus 1. N minus 1. Then p plus plus. Fine. When p equals to 1 means we are in the pass 1. Fine. Now take a look for the comparisons. So for I equals to, we don't start this loop from 1 because we have started our array index from 0. So accordingly this I has to start from 0. See, if I is started from 1, I would have taken this loop maximum limit till n minus p. Because why I am saying in the previous discussions, you can see here number of passes are n minus 1, number of passes are n minus 1, and the comparisons are n minus p. In each pass n minus p comparisons we are doing. If you start the comparison index from the comparison value from 1, then 1 to n minus p is going to cover the number of times as n minus p. But if I start from 0, it has to be n minus p minus 1. That's what. So here I am taking 0 and I is less than n minus p. You understood now why I am now taking equals to here? Because it is starting value is 0. If it is 1, I should have taken here as equals to. Fine. Now what I have to do? I have to compare. Which one? First two elements. If the first element, that is A of I, is greater than A of I plus 1. If the first element is greater than the next element, what we have done? We have swapped it. So temp equals to A of I. What are the elements we are swapping? AI and AI plus 1. AI plus 1. Then AI plus 1 equals to temp. Fine? Close this. We are closing this if statement here. Whenever the previous element is greater than the next element, then we go for the swapping. This entire process is for swapping. Fine? Then close this ith loop, and you can also close the number of passes loop. So with this particular segment, we are going to sort the entire array. But we have to display it also. Process is done, but we have to display it. So let's go to the next. Now we are going to display. We are going to display sorted array. How do we display? Because you can see that in the same array only we made all comparisons. We have entire sorting process is done on the same array. Whatever the array we have taken for the input. Okay. So for I equals to 0, I is less than n, I plus plus, Within this, printf percentage %d, I just wanted to display the elements line by line, use the slash n of I. Fine, close it. As we have used the int main, so return some integer value, then you can close the program. This is only display statement. Fine, I'm just displaying the elements line by line. So we were not in the need of any further variables, you can just close this. Fine. So after the program, we are going to understand the analysis part. Let me discuss about the best case. What is the best case time complexity of the bubble sort? What is the best case time complexity of the bubble sort? Best case occurs when we have already sorted sequence of elements. 5, 10, 15, 20, 25. Okay, already the elements are sorted, then the best case occurs. So we just compare these two, but there is no swap. No swap. Same we compare here, no swap. Between every adjacent element you can see, because it is already in ascending order, no? Always the previous element is smaller than the next element. Definitely there will not be any swap. Okay? But the program what we have written, that's not the optimized bubble sort. Optimized means in the first pass, if there is no swapping, see in the pass one, you can see here the same process you apply it. In the pass one there is no swapping. When there is no swapping in the pass one, definitely there will not be any swap in the pass two also. So we have to make sure, if in case in pass one there is no swapping, no need to continue with the process. So what modifications we have to do for our code? Very simple. What modifications are we going to do? Just take one variable, as flag, set it to the 0. When p equals to 1, we get inside this loop now. If a is greater than ai plus 1, that means the previous element is greater than the next element. Then inside this if statement only, you make your flag equals to 1. You make your flag equals to 1 inside this. Because there is a swapping. When there is a swapping, at least one swapping is there, flag will set to 1. Okay? After coming out of this ith loop, okay, you check it. If flag equals to 0, see, if at least one particular element got swapped with the next element, the flag is setting to 1. After the first pass, if the flag remains 0 means what? There is no swapping. You remember this. This condition I am checking. Where I am checking? Outside this ith loop. So in the ith loop, I am going to make a comparison between every two elements of an array. Inside the first pass, but I am making a comparison within every adjacent elements in an array. If the flag is setting up to 1 means there is a swapping, then again I have to continue with the same process. If flag equals to 0 means what? There is no swapping. Then simply just break it. Break from rest of the passes. Fine. In this case, what is the time complexity? Only how many comparisons we did? n minus 1 comparison. Pass 1 means we know n minus 1 comparison. Within this, we got to know that array has already been sorted. So what is the best case time complexity? Big O of n. Big O of n. If I have to go for the worst case, worst case means what? Complete reverse order we have. Okay. So in the first case, how many comparisons? In the past one, how many comparisons we are making? How many comparisons as per this example? N minus 1 means n equals to 4. So 4 comparisons. In pass 2, pass 3, pass 4. We have seen in the previous example, if number of elements are 5, we need to have 4 passes only. So here it is n minus 1, here it is n minus 2, n minus 3, n minus 4. Just sum it. So it's going to be n into n minus 1 by 2, which is nothing but big O of n square. So the worst case time complexity of the bubble shot is big O of n square. Fine. Let's meet in the next session.